When LTX 2.5 shipped on August 11th, the headline numbers required massive enterprise compute. The developers demonstrated the 22 billion parameter model, rendering 10 seconds of 720p video in 6.8 seconds, a benchmark achieved on a pair of high-end GB200 data center accelerators. 8 days later, the focus shifted to what the same model could do at the opposite end of the hardware spectrum, a single 16GB laptop GPU. The local test yielded 3.88 seconds of finished video. That is 97 frames at 832 by 480 resolution, generated in one pass with its own native audio score. The entire render took exactly 77.7 seconds. Solid green elements represent values physically measured on this bench and backed by a receipt. Dashed violet represents unverified upstream launch claims or untested assumptions. Executing a 22 billion parameter architecture for both video and audio inside a strictly constrained 16GB envelope creates a significant computational bottleneck. Fitting this model on local hardware is not achieved through casual tuning. It requires a mathematically precise deconstruction of the node graph. This analysis ignores community rumors and focuses strictly on the physical evidence of what actually executes. To maintain a stable render on 16GB hardware, users must rely entirely on tested, receipt-bound realities rather than unverified assumptions. Managing this process begins with identifying the absolute physical boundary of a consumer graphics card. A 16GB GPU provides a strict, addressable ceiling of 15.92 GB once system overhead is accounted for. This gauge tracks peak memory across 16 receipted runs. Every single test landed in an immovable band between 15.47 and 15.60 GB, regardless of changes to user settings. With the card addressing 15.92, the remaining safety margin is exactly 0.32 GB. That tight operational window means a single inefficient node or slight parameter deviation will immediately trigger an out-of-memory crash. The 0.32 GB gap establishes 16 GB as the model's absolute physical floor. Beyond memory, the architecture itself presents roadblocks. Standard local deployment methods fail to load the model out of the box. The first failure point is the text encoder. Standard Comfy UI loaders do not recognize the specific Gemma 4 12 billion parameter encoder LTX 2.5 uses. This is resolved by patching the architecture list to explicitly recognize the Gemma 4 designation. A second failure occurs because the stock system natively ignores any tensors stored above rank 1. This causes 3 crucial parameters stored in BF16 format to be bypassed entirely. One of those bypassed tensors is the dedicated audio embeddings character, the bridge between video output and sound generation. Without forcing a dequantization patch for these specific tensors, the model's native audio path cannot function. Since native audio is the core feature of version 2.5, deploying this specific pipeline fix is a requirement for the model to exist in its complete form. Tuning the performance often starts with the assumption that lowering model quantization will provide significant memory savings. This comparative chart shows a direct A/B test of identical recipes, swapping the Q5 quantization for a lower Q3 version. Dropping to Q3 saved only 0.05 of a gigabyte in VRAM, while increasing the render time by 26%. On this architecture, quantization acts as a speed lever. It provides no usable VRAM headroom. Preventing silent system failures requires adherence to the strict mathematical rules of the node graph. The spatial constraints are absolute. Both canvas pixel axes must divide by 32, and the total frame count -1 must divide by 8. There is also an unavoidable audio processing tax. The audio VAE loads and consumes memory even during silent video generations. Operating within these strict mathematical boundaries is the only way to avoid the crashes associated with standard local AI intuition. Even a perfectly patched and mathematically correct graph cannot cross certain architectural walls on 16GB hardware. Attempting a 161-frame multi-shot sequence causes memory usage to spike past 18 GB, exceeding the card's capacity. Utilizing in-graph 2x upscaling forces a massive decode process that results in an immediate failure. These boundaries define the absolute functional limits of the 16GB hardware class. Identifying these limits reveals the distinction between a successful technical execution and a usable creative output. Every receipt-backed run in this test was a technical success, producing a valid, memory-compliant video file. However, the data repository still marks these runs as eyeball pending and promotion-ready false. In this context, a working pipeline is one that functions and fits into memory. It makes no claims regarding the aesthetic quality of the output. This grounded reality is the alternative to unverified launch claims and social media hype. True optimization is achieved by separating rumor from workflow, using written, tested data to establish a functional pipeline for the 16-gigabyte community.